Acid-base titration is a fundamental technique in analytical chemistry that allows us to determine the concentration of an unknown acid or base. Picture this. You have a solution of hydrochloric acid and you want to find out its molarity. You'd use a sodium hydroxide solution of known concentration as your titrant. As you slowly add the NaOH to the HCl, you're watching for that color change, often with the help of a pH indicator like phenolphthalein.
Let's continue with the example. 50 milliliters of 0.05 m HCl was titrated with 0.1 m NaOH. Calculate the pH of the solution at first, initial point, second, after addition 10 milliliters NaOH, third, after addition of 25 milliliters, and lastly, after addition of 25.1 milliliters NaOH.
Let's solve a titration problem to find the initial pH of a solution. In this problem, we have 50.00 milliliters of 0.05 molar hydrochloric acid that will be titrated with 0.1 molar sodium hydroxide. Let's visualize our setup. We have our Erlenmeyer flask containing the hydrochloric acid solution, and above it, we have our burette containing the sodium hydroxide solution. However, we're only interested in the initial point. That is, before we add any sodium hydroxide. To find the pH, let's follow these steps. First, we'll calculate the initial moles of HCl. Then, we'll determine the H+ ion concentration. And finally, we'll calculate the pH using the pH formula. Let's start with step 1. To find the moles of HCl, we multiply the concentration by the volume. First, we need to convert our volume to liters. 50 milliliters is equal to 0.050 liters. Now we can multiply 0.05 molar by 0.050 liters. Now for step 2. HCl is a strong acid, which means it completely dissociates in water. The dissociation equation shows that 1 mole of HCl produces 1 mole of H+ ions. Therefore, the H+ concentration is the same as the HCl concentration, 0.05 molar. Finally, let's calculate the pH. Remember, pH is equal to the negative logarithm of the H+ concentration. So we take the negative log of 0.05. This gives us a pH of 1.30. This pH value makes sense because, first, we're dealing with a strong acid, so we expect a low pH. And second, the concentration is between 0.1 and 0.01 molar, so we expect a pH between 1 and 2. Therefore, the pH of the solution at the initial point of the titration is 1.30. Let's calculate this step by step. First, let's find the initial moles of hydrochloric acid. This is equal to the concentration 0.05 molar times the volume 0.050 liters, which gives us 0.0025 moles of HCl. Next, let's calculate the moles of sodium hydroxide added. That's 0.1 molar times 0.010 liters, which equals 0.0010 moles of sodium hydroxide. When we mix these solutions, hydrochloric acid and sodium hydroxide react in a 1-to-1 ratio to form sodium chloride and water. Since we started with 0.0025 moles of HCl and used up 0.0010 moles in the reaction, we have 0.0015 moles of HCl remaining. Now we need to consider the total volume after mixing. The total volume is 50 milliliters plus 10 milliliters, which equals 60 milliliters or 0.060 liters. To find the new concentration, we divide the remaining moles of HCl by the total volume. This gives us 0.015 moles divided by 0.060 liters, which equals 0.025 molar. Finally, since hydrochloric acid is a strong acid that dissociates completely, the hydrogen ion concentration equals the acid concentration. The pH is the negative log of the hydrogen ion concentration, which is negative log of 0.025, giving us a final pH of 1.60. We need to find the pH after adding 25 milliliters of 0.1 molar sodium hydroxide to 50 milliliters of 0.05 molar hydrochloric acid. Let's visualize this titration setup. We have our Erlenmeyer flask containing the hydrochloric acid solution, and we're adding sodium hydroxide from the burette. When these solutions mix, they undergo a neutralization reaction. Let's start by calculating the moles of hydrochloric acid we have. To find moles, we multiply concentration by volume. The volume needs to be in liters, so we'll convert 50 milliliters to 0.05 liters. Multiplying 0.05 molar by 0.05 liters gives us 0.0025 moles of hydrochloric acid. Now let's calculate the moles of sodium hydroxide added. Again, we multiply concentration by volume. 25 milliliters is 0.025 liters. So 0.1 molar times 0.025 liters gives us 0.0025 moles of sodium hydroxide. Looking at our results, we can see that we have 0.0025 moles of both hydrochloric acid and sodium hydroxide. This means we've reached the equivalence point where the acid and base have completely neutralized each other. The products of this reaction are sodium chloride, which is a neutral salt, and water. At the equivalence point of a strong acid-strong base titration, the solution is neutral. This means that the concentrations of hydrogen ions and hydroxide ions are equal, and the pH equals 7.00. To summarize, when we add 25 milliliters of 0.1 molar sodium hydroxide to 50 milliliters of 0.05 molar hydrochloric acid, we reach the equivalence point where the acid and base completely neutralize each other. At this point, the pH of the solution is 7.00. We need to find the pH after adding 25.1 milliliters of 0.1 molar sodium hydroxide to 50 milliliters of 0.05 molar hydrochloric acid. Let's start by calculating the moles of HCl we have initially. To find moles, we multiply concentration by volume. That's 0.05 molar times 0.050 liters, which equals 0.0025 moles of HCl. Next, let's calculate the moles of sodium hydroxide added. Using the same equation, we multiply 0.1 molar by 0.0251 liters, giving us 0.00251 moles of sodium hydroxide. When these solutions mix, hydrochloric acid and sodium hydroxide react in a 1-to-1 ratio. The balanced equation is HCl plus NaOH yields NaCl plus H2O. Let's determine if we have excess acid or base. We can subtract the moles of HCl from the moles of NaOH. We get 0.00251 minus 0.0025, which equals 0.00001 moles of excess sodium hydroxide. Now we need to find the concentration of this excess sodium hydroxide. First, let's calculate the total volume by adding the volumes of both solutions. 50.00 plus 25.1 equals 75.1 milliliters, or 0.0751 liters. The concentration of excess sodium hydroxide is the moles of excess divided by the total volume. That's 0.00001 moles divided by 0.0751 liters, which equals 0.000133 molar. Finally, we can calculate the pH. First, we calculate pOH as the negative log of the hydroxide concentration. That's negative log of 0.000133, which equals 3.88. Then, pH equals 14 minus pOH, which is 14 minus 3.88, giving us a final pH of 10.12. Since our final pH is greater than 7, this confirms that we have an excess of base in our solution. This makes sense because we added slightly more sodium hydroxide than was needed to neutralize all of the hydrochloric acid.